Hi everyone, welcome to the introduction video of Lab 7, Kalman Filter. Um, so what we are going to do today is to implement a Kalman Filter on the FPGA, okay? So the Kalman Filter is basically um, estimate of the state of the system based on our input and our observation of the state here, okay? So the linear system is described by this equation. We have the column vector here as a state, and also we have the this f describe the characteristic of the system, and also we have the input multiplied by the speed. This is also the characteristic of the system. And sometimes we have the noise here. So in this lab, we just describe it as the Gaussian distribution noise here. Okay, and also we have the estimation the based on the state. Here we assume that we cannot directly check the state, but we only have a estimate. We only have a observation here with some noise here. Okay. I will not go into the mathematical details about how the filter works, as they are introduced in the lecture. So we directly go to the lab implementation part. So in the lab, we are dealing with a system like this. Uh, we have a state vector. So this is basically a linear system describing a vehicle, I guess here. Okay, so the state is a 2 by 1 vector. We have the position of a vehicle and the velocity of a vehicle. And the input, let me see. Oh, input should be just a scalar in this situation. It's just the acceleration of the vehicle. And by the Newton's law, we have the linear system described like this. Okay. So what are we gonna do is we know our input of acceleration u here. We also know the observation z here, and also we know the initialized state of position, the velocity of the vehicle, right? We assume they are all zero here, okay? And we will go over these several equations many times, and then we will have our xk as the output of this design as the estimation of x. Okay. So let me see what. So what you will be coding is basically you do these all of these matrix operations. So the xk minus 1 is your previous x, and your xk is your next x here. Okay. So note that we have minus and plus here. They are separated registers. Okay. So let me see. 1, 2, 3, 4, 5, 6. You will have six. You will have six equations to calculate here, and I would recommend to just use the state machine here. For example, you can have one state for each of these equations. So like, and also you will have the state for the sampling at the very first and the very last state for the output. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. In total, you can have 8 states for the whole design. And for the first design, you just let's just go to the code, okay? So for the first state, you will just sample all these input, okay? Keep these input to some registers and save them. And then for the first state, you calculate your x multiplied by f, and also you multiply the b with the u. Of course, we are using the matmul 2x2 module here. This is already instantiated for you, okay? So you don't have to call this again in your design. And we have we have created some wires for the input and the output of this matmul module. And these wires are connected to these registers here. Okay, so for example, if you want to calculate f times x, you will assign the value of f into this into this register multiplication in, and also you will assign x into this multiplication in with index 1 here. Okay, we have the two input of the multiplication, right? They are in I-0 and I-1 here. In the second dimension here, these are just the 4 entries of the 2x2 matrix. Okay, and also once you calculate f times x, this matmul module is in idle state, right? It's no longer used, and then you can use this to calculate the b times u here. And then, of course, you need to save the output of this multiplication into some temporary registers and hold the values until you use it later, right? Yeah, so as you can see, in one state, you will have multiple multiplications and something else. And since we only have one multiplier here, okay? You will do these operations one by one, okay? So in that case, for each state, uh, it's probably likely that you will not be able to finish this equation within one clock cycle, okay? So you will need basically several cycles for each of the state and each cycle you will do one operations, at least one multiplications here, okay? Yeah, and once you finish the first state, you will go to the next state, do the same thing just for the different registers, and then go on until you calculate the last one. Here you will have your xk minus ready for the output. Okay, you output it to the xo. And also we have the no. Why is like that? Okay, so for our design, you will have, let me see, you should have 1000 input in the implementation on the board, okay? Let me see where it is. Can't find it. Okay, here, you will totally have 1000 input, okay? But you are not necessarily to use all of them. This is actually based number of input you will use is actually based on your latency and your delays here in your design here. Suppose like you take 20 cycles to calculate these once, and then maybe you will just sampling every 20 cycles for the input for the yield, right? Um, so 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 as a so for the 1000 input, the n will be from 0 to 999 here, and for the sampling, you will also have the corresponding u here in that uh, input elements here. Okay, so for the sampling state here, you wanna keep the save the value of n and u. Of course, you will be using the u for the calculation, and you will keep the n until you have you keep it until your output state here. Okay, so for the output state, you will output X as the output, and you will output N as the output. This NO is telling the testing program that which you are using for calculating this X. Okay, so for example, in the first state, you save the N, and then you will assign the N you saved, you sampled, until the last state, and put it as an output as NO here. Okay, and for the next round, you will go over again, go back to N, save the sample the N and the U and so on until you have another output. You will assign N to NO here, and you will assign your X to your XO here. Okay, so this is really basically iteration is a loop in like an infinity loop. Okay, until you run out all of your input. Basically that's it. So I guess this is easier than your previous lab, right? You don't have to deal with any complicated logic there. Um, okay, so for undergraduate and for graduate students, you are required to have at least 5 or 10 output here within 1,000 cycles. I guess this is a pretty easy requirement as you will. So for example, if you want to have 10 outputs, maybe you just have a delay less than 1,000 cycle, 100 cycle. That should be enough, right? I guess you should be able to do this calculation within 100 cycles. Of course, you can have some even faster design, like you can have pipelining, you can have multiple matmul, but it is not necessary. Okay. I guess that would be it. Okay. Okay. Another thing to notice, you will have 3 block RAM in this design. Okay. The settings are listed here. Don't forget to do this. And also for the testing program, you will have codec, plasmagram, and also you have the clock cycles of your design. And these numbers can actually be inferred from your design, okay? Like how many states you have and how many clock cycle in each state, you just sum it up, and you should be able to know what is your best sampling state. Also, of course, you can tell it from the simulation, right? You just write a very basic simulation, give one N and one U and one of these input, and you will see how many cycles later your X and N is ready for output. That's another way to calculate these numbers. And of course, you can just try different numbers in the board. Like for example, I have 10 here. You can try 10 or 15 or 18 or 25 or anything else. Just and for each of these tests, you will have um, the testing program will tell you um, what is the error compared to the original data here. Okay, and you want to find what is your minimum error and screenshot it and attach it to your report. Okay. Yeah, I guess that's it for our introduction video. And good luck on your design. Hopefully you can finish it all within your lab session on Tuesday. And yeah, that's it. Thank you.